Let's discuss Unit 7 solutions. A three-dimensional array in C++ is declared as int a of A, B and C. Consider that array elements are stored in row major order and indexing begins from 0. Here the address of an item at the location A with 3 indices RST computed in terms of word length W of an integer is. In general, array will be stored in continuous memory location. So if you take a 2D array that is only with rows and columns, you can refer this to 0, 0. Since it is row major order, table will be in this format. This is row and this is column. So row 0, 1, 2 and column 0, 1, 2. So 0, 0, 0, 1, 0, 2, it goes on. Similarly 1, 0, 1, 1, it goes on. This is the way it will be accessed if it is row major order. Here there are 3 dimensions to an array. The last 2 dimensions will be the row and the column respectively. What is this A, the first index? It will be that particular block. Say for example, if you take this to be the 2D array. So this is row 0 and row 1. This is column 1 and column 2. Here there is another dimension. This will say to which block does these rows and columns belong. We can term it as block, or we can say it is a set of 2D array. So this block will have a set of 2D array. This block might have a set of 2D array. Let's interpret this representation first. A with index A, B and C. Index A denotes the number of 2D arrays. It will be ranging from 0 to A minus 1. So usually this will be called as block. That blocks row and that blocks column. B will be the number of rows. It will be ranging from 0 to B minus 1, and C will be the number of columns 0 to C minus 1. The base address, that is the first address, will always be with index 0. So 0 will be there in every index. It will be block 0, row 0 and column 0. Now they are asking there is an item in the location A of RST. It means it is rth block, sth row and tth column. Computed in terms of word length W. So once you find that location, you have to multiply it with the word length of integer W. Let's interpret A of R, S and T. What does this R say? The item is located at rth block. So this rth block will have a 2D array consisting of B number of rows and C number of columns. So I have to skip R minus 1 2D arrays which will include B number of rows and C number of columns. So I said the range will be from 0 to A minus 1 for block in this case. So if I have to access the rth block, it means I have to skip R minus 1 blocks. If I am in the 5th block, it means I have to skip 4 blocks. So if I say it's the rth block, it means A of R 0, 0. It means I am in the starting of the rth block. This is rth block, 0th row and 0th column. So now if I have to skip these many blocks, then I have to include both the rows and the columns count. So it will be R times of B rows and C column. How many positions should I move? I have to move R into B into C. When I say I have to move R blocks, it is including those rows and columns inside that block. So I can say A of R is reached in this position. Okay. Now I have to reach A of R sth row. Now the block is selected. So there is nothing we can do with the block. Now it is the usual 2D format. If I want to go to the 5th row, I have to skip 4 rows. Say for example, if I include this row, it will also include the columns. When I say it is A of R then S of 0, it means I am in my rth block, sth row and 0th column. Here R block is fine, we have already found. Now we have to calculate for sth row. So for sth row, it means I have to multiply S into the number of columns, which is C. So S into C will be taking me to the corresponding row. Now we will have R, S and T. Here we have reached rth block, we have reached sth row. Now we have to find the exact column. If I want to find it in 9th column, I have to skip 8 elements. So I can directly reach T. If you take R into B into C, then S into C, then T. Now I have to add all these things. R into B into C plus S into C plus T. This will actually be the correct location of the item. So where do you find this? It is in option number 2. It is perfectly matching. So they have taken rows into column into block, then column into row, then the column number. And the base address is given by A of 0, 0, 0. Since the index is beginning from 0, ampersand of A will tell you the exact address. Option number 2 will be the right answer. Now you can find there is something called W into. Since it is computed in terms of word length W, we are multiplying the whole set by W. This will actually give the address of the item in the location rth block, sth row and tth column. This is the way of interpreting step by step. Now there is a formula for this. Formula to access an element at A of I, j and k. This will be ith block, jth row and kth column. First B, we will add the base address. So let me expand here. Base address plus, if there is any storage size for the element, we can mention it. It is represented by W. Here they have used integer W into, in general, for this table we have m number of rows, n number of columns, and they have given some lower bound of m rows and n columns. I am not including those details inside. I am just giving you whatever is needed for this answer. Okay. So now m into n into the block I plus n into the column count into the row j plus k. For this problem, capital M is equal to B and capital N is equal to C. I is equal to R, J is equal to S and K is equal to T. Now if you substitute it here, you will get it. Instead of base address, they have given ampersand of 0th index, and instead of small w, here it is capital W. Next question. Suppose a circular queue of capacity n minus 1 elements is implemented with an array of n elements. Assume that the insertion and deletion operations are carried out using rear and front as array index variable respectively. Initially, rear is equal to front is equal to 0. The conditions to detect queue empty and queue full. What is a circular queue? It's a queue whose last position will be connected back to the first. It will be in the form of circle. You will have the element storage. Whatever you insert, it will be inserted in the rear position. Whatever you delete, it will be deleted in the front position. Just imagine a normal queue. Whoever enters first will be going out first. If you take stack, whichever comes last, that will be taken out first. So it is last in, first out. But here queue is first in, first out. Whichever enters the queue first will be coming out first. Okay. Insertion process is also called NQ and deletion process is called DQ. This insertion will take place like after inserting in the last position, the next element is inserted at first position. So let's start with queue empty condition. When can I say the queue is empty? when both front and rear end up in the same place, or when they have the same index, I can say the queue is empty. They have given initially both have 0, but queue empty condition will be when rear index is equal to front index. So wherever you find empty rear is equal to front, we will keep that option. The rest of the option can be ruled out. Now let's check what is queue full condition. Let me give you a small example. Take the index of rear to be 4 and front to be 0. There are totally 5 elements to be inserted. So I am inserting it from 0, 1, 2, 3, 4. So since I have not deleted anything, front is having the same 0th value. So when I insert all the 5 elements, this will hold the first element and this will hold the last element, which means it is holding the 5th element. If I want to delete, I will proceed with the first element. This example scenario is queue full scenario. How can I check this? I can check it with this condition, rear plus 1, that is 4 plus 1 mod n. 4 plus 1 mod 5 will be equal to 0. So this will be equal to front. There are 5 elements in the circular queue. The first element will be in front and the index will be 0. And now the last element inserted will be in the rear position and the index will be 4. For better clarity, I am changing it to element 1, element 2, element 3, element 4 and element 5. First I will insert in this position. Then when I insert my second element, the previous element will move here and the second will be inserted here. When I insert the third element, the first element will move here, second one here and the third one will sit in the rear position, rear index correctly. Similarly, when I insert fourth element, the first element will come to this position, that is index number 1. So this is index 1, index 0, index 2, index 3 and index 4. When I insert the fifth element, the first element will be pushed to index 0. So from the back, it will be pushing it little by little to the front. So in that way, we make a computation with rear plus 1 mod n is equal to front. This will say whether the queue is full or not. So I get a value of 0 in this example, which is the value of front. It is rear plus 1 and here it is front plus 1. So obviously we will drop option 4. Option 1 will be the right answer. Next question. Consider a hash table of size 7 with starting index 0 and a hash function 6x plus 3 mod 4. Since they have placed the options in horizontal manner, let me also depict the hash table in horizontal manner. It is starting with the index 0. So we have started the slot numbering from 0 and ended up at 6. There are totally 7 slots available. The hash function will be 6x plus 3 mod 4. Assuming the hash table is initially empty. Which of the following is the content of the table when the sequence 1, 3, 8, 10, 5 is inserted into the table using closed hashing? What is closed hashing? Closed hashing is also called open addressing. Here if collisions occur, they will be stored in another slot. There is other type of addressing in which if collisions occur, they will be stored separately. But in open addressing or closed hashing, when two or more contents of the table go to the same slot, if there is already an element present in the slot, it will be stored in another slot. Here underscore denotes an empty location in the table. Now let's compute this. 6 into 1 plus 3, this is 9 mod 4. 4 2s are 8, so remainder 1. So 1 will be placed in the first slot. Then we will compute for 3. 6 into 3 plus 3, 18 plus 3, it is 21 mod 4. So 4 5s are 20. Again it is coming to the first slot. So since first slot is already occupied, we are just moving to the next slot. 3 is occupying the second slot. This is the use of closed hashing. Next we have 8. 6 into 8 plus 3, 48 plus 3 will be 51 mod 4. So 4 12s are 48. Then the remainder will be 3. So the third slot will have 8. Then 10. 6 into 10 plus 3 will give 63 mod 4. 15 into 4 will give 60. Again there is a remainder of 3. So we will move to the next slot and store 10 in fourth slot. Then we have 5. 6 into 5 plus 3. This will give 33 mod 4. 4 8s are 32. Remainder will be 1. And here 1 is occupied, 2 is occupied, 3 is occupied, 4 is occupied. And so we are placing 5 in the fifth slot. Wherever the slot is free, use underscore and then write the elements in the horizontal way. So this is perfectly matching in option number 4. So option number 4 will be the right answer. Next question. Given below are two statements. One is labeled as assertion and the other is labeled as reason. The AVL trees are more balanced as compared to red black trees. But they may cause more rotations during insertion and deletion. This is true statement. The heights of AVL trees as well as red black trees are generally same, but AVL trees require frequent rotations to maintain their balance. So because of that they say they are more balanced. Okay, the statement is true. The reason: a red black tree with n nodes has height that is greater than 2 log 2 n plus 1 and the AVL tree with n nodes has height less than log 5 of root 5 into n plus 2 minus 2. This 5 is called the golden ratio. So red black tree will have a height less than or equal to 2 log n plus 1 and AVL tree height will be less than log with the base 5 root 5 n plus 2 minus 2. So AVL's comparison is less than, that is right. But here they have given red black tree has height that is greater than, which is wrong. Actually it is less than or equal to, since this part is wrong. It is less than or equal to, we mark R to be false. So we are not getting into option 1 and option 2. We are ending up with option 3. A is true but R is false will be the right answer. Next question. Given below are two statements. Let f of n and g of n be asymptotically positive functions. The following conjectures in the sense guesses, something of that sort, are given. So statement 1 says f of 1 is greater than 1, which means f of n is a positive constant. By the definition of big O, f of n will be less than or equal to c into g of n for some positive constant c. From this we can conclude g of n is greater than or equal to 1 by c f of n, and this statement is actually a definition of transpose symmetry. The statement will be like f of n equals to big O of g of n if and only if g of n is equal to omega of f of n. So statement 1 is true. Statement 2, f of n is equal to big O of g of n. Now they are applying log to this and they have given log of g of n is greater than or 1 for all sufficient large n. F of n is less than or equal to c into g of n. Now I am applying log here. Log of f of n is less than or equal to log of c into g of n, which is less than or equal to log of c. I am applying log. Since I am splitting it, I have a plus here, log of g of n. From here, I can say it's less than or equal to log of c and log of g of n plus log of g of n. This is because they have given log of g of n is greater than or equal to 1. That's why we are bringing this. We will bring log of g of n outside. So log of c plus 1 into log of g of n, which means log of f of n is less than or equal to, this is in the form of constant into g of n, log of g of n. Now here this is equivalent to this part and this is equivalent to this part. So here, since log of g of n is greater than or equal to 1, instead of 1 I am placing it. This is like log of c into 1. This is again like in the form of c into g of n. So instead of c, here it is log c, and here instead of g of n it is log of g of n. So I am just placing it back like big O. So from big O I took this part. So from this part I am again making it as big O. Okay. I could just simply say the statement 2 is also true. Option number 1, both statement 1 and statement 2 are correct, will be the right answer. Next question. Given below are two statements. One is labeled as assertion and the other is reason. Assertion is, it is possible to create doubly linked list using only one pointer with every node. There is a supporting statement. It is possible to implement a doubly linked list using a single pointer per node by storing XOR of addresses of the previous and next nodes. So the single statement is split here. They say there is a possibility to create doubly linked list using only one pointer. So this is true, and how they create is by storing the XOR of addresses of previous as well as next node. So if you take this to be the doubly linked list, usually if this is the node, this will be the link to the previous node and this will be the link to the next node. This is also true. This becomes the reason of A. This method of storing the XOR of the address is actually memory efficient because the list uses bitwise XOR operation to save space for one address. Instead of actual memory address, every node will store the XOR of address of previous and next node. So from this we can conclude that both A and R are true and R is the correct explanation of A. Option 1 will be the right answer. Next question. Consider the following statements about heap sort algorithm. Max heapify procedure, which runs in O of log n time, is the key to maintaining the max heap property. This will maintain the max heap property as well as this runs in O of log n time. This is true. The build max heap procedure, which runs in O of log n time, produces max heap from an unordered input array. Actually, the content about the procedure is right, but the running time is wrong here. So we will mark it as false. Build max heap procedure runs in linear time. The max heap insert, which runs in O of log n time, implements the insertion operation. This is true. A and C included in any answer? Yes, it is included in two options. I am removing the rest of the option here. But when I say B is wrong, I automatically say 4 is also wrong. So option number 2, A, C only will be right. Then what is wrong with statement D? The heap increase key procedure runs in O of n log n time to set the key of new node to its correct value. Again, the explanation of the procedure is right, but the time is wrong. There are 4 procedures: max, heap, insert, heap extract max, then heap increase key, then heap maximum. All these 4 procedures take same amount of time. I mean, they run in big O of log n time. It means whatever time C takes, the same time D will take. So it is not n log n, it is big O of log n. With these procedures, we can implement a priority queue. The heap sort procedure runs in big O of n log n time and it sorts an array in place. Next question. They have given 4 statements and they are asking which are right from the options. If some NP complete problem P is in P, then P is equal to NP. The depiction will be, this is NP and this is P. This part will be NP hard and here this part will be NP complete. This is in the case where P is not equal to NP. Now when P is equal to NP, the scenario will be, this will be NP hard, but here P is equal to NP and it is approximately NP complete. When we take this depiction into consideration, if some NP complete problem P is in P, then P is equal to NP is what this diagram says. So A is true. We can remove option 2. Next, TSP, traveling salesman problem is in NP. This is actually true. It is in NP. To check if the total cost of edges of the tour is minimum, it can be completed in polynomial time. That's why we are marking it to be true. The next statement is satisfiability problem is in NP. SAT is also in NP because any assignment of Boolean values to Boolean variables that is claimed to satisfy given expression can be verified in polynomial time by a deterministic Turing machine. So this is also true. A, B and C are true. They have given only 3 statement possibilities. So option number 1 will be the right answer. 3 and 4 are also ruled out. Hamilton circuit problem is not NP complete. This is false because Hamilton circuit problem is NP complete. Though we have seen that C is right, let me give you one more point. Satisfiability problem as well as circuit satisfiability problem, both are NP complete. Next question, match list 1 with list 2. The running time of straightforward recursive method to compute the nth Fibonacci number Fn. When we say something is in the form of recursion, we go with the power of some 2 or we take exponential time. We can mark 5 power n. Option A will be mapping to 4. Option 1 and option 3 are ruled out. Next, the running time to compute Fn using memoization. So what is memoization? It's an optimization technique to speed up by storing results of expensive function calls and return cached result when the same inputs occur again. So when we use memoization, the running time will be reduced. From this we can say B will be mapping to 3. So A4 and B3, we will even rule out 4. So option number 2 will be the right answer. Next statement, the running time to compute Fibonacci number Fn using only integer addition and multiplication. For that it will take big O of log n. So C will be mapping to 2. The running time to determine an optimal bitonic tour. What is bitonic tour? This minimizes the total amount of horizontal motion with ties broken by Euclidean distance. Then what is optimal bitonic tour? The bitonic tour with minimum total length. So when you go for tour, you will already have lots of movements. So it will end up with a complex time. We find big O of n square is high here. So we are assigning option 1 to D. The next question. Match list 1 with list 2. First one is parallel FFT, fast Fourier transform. What is parallel FFT? From the name you can understand, this will segment the FFT into groups of identical parallel operations. So this will have parallel operations that can be performed concurrently and independently. This will take log n time and so we are mapping A to 3. 2 and 4 are ruled out. Next we have iterative FFT. So there is something called recursive FFT where recursion takes place. This uses the classic divide and conquer method. But iterative FFT is little bit different from recursive because this saves the recursion stack space and this will take n log n time. So B is mapping to 4 Option 1 is also ruled out. Option number 3 will be the right answer. Next is evaluation of polynomial at n points by Horner method. This will take n square time. C is mapping to 1 and product of two polynomials that are represented in point value form. This will take n time. The reason why it takes less time is because of the point value form. Now let us see what is the point value representation of polynomial. So let's take two polynomials A and B and the product will be C. Let me show you the representation first. This will be in the form of x0, y0a, then x1, y1a until the end. I am not ending up, I am just showing you the representation alone. The polynomial b will be of the form x0, y0b, x1, y1b. The product a into b will be in the form x0 will stay and the product of y0a and y0b will be taken. x1 will stay, y1a and y1b will be taken here. So this is the way the product will be computed. Then what is point value representation? It's a set of n point values pairs. The representation of x0, y0, x1, y1 is actually in the form of point values. This product computation will take only theta of n time. We are aware of the product of polynomials using coefficient form. When it is done using coefficient form, this will take n square time. Now you can understand how much it is efficient. So this is about point value representation. Now a little bit of detail about Horner method. We can say as Horner's rule polynomial. So what is Horner's rule polynomial? Let's take a polynomial a0 plus a1x plus a2x square plus up to an x power n. This will be represented as a0 plus, I am bringing this x outside and I have a1 plus, then I am bringing another x outside, a2. When you multiply these two, you will have a1 into x. When you multiply x with these two, you will get a2 x square plus x into a3, it goes on till x into a power n minus 1 plus x into an. This evaluates n degree polynomial with n multiplications and n additions. So additions are this and multiplications are this part. It's an efficient algorithm to compute value of polynomial. With this we are completing Unit 7 questions.